Okay guys, hey, welcome back to part 2 of our software. I had to split this one up just because we were covering quite a lot in this little project. We got two big deals happening, the ADC as well as the LCD happening together. Then we're using a new compiler. We're not using the CCSC compiler, we're using the High-Tech C. So we're going to go ahead and look at the ADC part. If you haven't caught the first half of this video, I suggest you go back and watch it. It covers pretty much everything up till now, which is the LCD screen and how it's implemented and built and written to and all that stuff. So this is we're going to pick up with the ADC right here and its functions and how it works. We're going to start off with the initialize A2D function. What this is we're going to be setting the ADC configuration registers 0 and 1. And if we want to go ahead and pop back to our ADC, if we click on our ADC module configuration for our PIC 16F676 chip, or whichever chip that you may be using, if you scroll on down till you find your ADC con registers, which is your configuration registers for the ADC. What you'll find is in the configuration 0 register, at least for this chip, you'll find that there is an AD on bit. This turns the ADC on and off. This is helpful if you're doing battery stuff, like let's say your microcontroller is being run by a battery and you want to conserve battery energy. You don't want to turn the ADC module on until you need it. Because it does burn a little bit of power to turn it on. So that allows you to turn it on and off. Our application, we're just going to run it off of a power supply, so it doesn't matter. We'll turn it on, leave it on. There's the go done pin. What this means is this: if you set this to 1, it will initiate a I want to say actuation. No, that's not right. Acquisition, I guess. It'll initiate an acquisition cycle to where it will take a measurement of the analog port that you've declared. And then it turns into basically an output port and will output as 0 when it has successfully finished taking an acquisition. So you can put controls in that maybe wait till that's done, just in case you're doing like maybe a an interrupt driven system to where you don't have time to sit and wait on it to finish. You need to go ahead and start the acquisition, go do some other stuff, and come back to it later when it's finished. You will monitor this pin. For us, we're not doing anything like that, so we don't need to monitor it. So we'll just set it to a 1, and then when it's done, basically. The next 3 bits are your channel select. So everything from 000 to 111, you've got channels 0 through 7. That's your channel select bits portion of this. You've got your voltage configuration, which your voltage configuration is you can have this either tie its voltage reference to an internal VDD to basically the power of the chip, or you can have a separate external voltage reference it chooses one of the pins to do that. And if you want to know which pin it is, if you go back up to your ADC, it has it shown right here in this convenient little block diagram. Shows that your V reference is basically your RA1 pin. Well, it can be configured as a V reference. Now, those of you that don't know what you would use this for, an ADC has to have a reference so that it knows basically how many volts per bit that it's measuring. Essentially, this one is a 10-bit voltage regulator. Our voltage reference I'm tying to internal VDD. Well, the VDD that I'm supplying it with is 5 volts. Okay. So basically, if we grab our spiffy little calculator, if we have 5 volts and we divide that by basically 10 bits, which if you do a 10 bit, that's 2 to the 10th, so that's 1024. So we're going to take 5 volts, divide it by 1024, and basically for every digit, so to speak, from 0 to 1024, for every digit of that, for every increment, you're going to have about 4.88 millivolts per digit. So if you take an ADC acquisition and it sends back an integer number of 1, that means that it measured approximately 4.88 millivolts is what it's measured. And then obviously if it's 2, it's 2 times that, and 3 times that, and 4 times that. Is how that conversion works. If I change my reference, if I make the reference an external reference and I put an external reference of, I don't know, 3.3 volts, let's say, is the external reference, You divide that by 1024, and now we're about 3.22 millivolts per digit, per increment, I guess you could say. So that's what the voltage reference is for. And you, like I said, you can have maybe an external voltage, and sometimes it'll be the same voltage as what you're running at. It'll be 5 volts. But you know that if you use an external voltage reference that's a precision voltage reference, let's say, it will be, it's not real noisy, because a lot of noise can mess with your ADC and throw off your readings. So you might want to put something that you know is decoupled welly and has lots of aggressive filtering in it. So you may get like Linear Technologies makes them for example. You could get one of their voltage references and stick it out there, and that way you know that you've got a pure 5 volts with no noise on it. That would be another reason to help improve accuracy of your ADC. So essentially, you know, but like I said, for our application we're doing something simple. I'm just tying it to internal VDD is what that bit's going to be set for, but that's what that does. Your ADC format, which this does, is this, you can have it formatted in basically big Indian or little Indian. You know, your India Cs, which way you want it to be. And that's what this is. It shows it right here. This is the AD result format. If you set that bit to 0, it'll format it to where the MSB is back here, and then it goes to the LSB is in the 6th bit of the lower address. Or you can set it the other way, and it just basically mirrors it. It flips it over to where the MSB is now the 2nd bit in the address H register, and the LSB is bit 0 of the address low register. So yes, there are 2 registers. There's 2 8-bit registers that are implemented that it spans across, and you can choose whether it's right aligned or left aligned, whichever way you want to do it. We have chosen right aligned. Apologize. We've chosen to set that as 1, so it's left aligned is what that's for. So that's basically your ADCON 0 register. And what we do in our init is we set it to a hex 80, which will basically put a 1 here at bit 7. It sets bit 7 as a 1, and the rest is 0. So it basically clears everything out, turns it off, makes sure go done is initialized to 0. The channel will be initialized to channel 0, and then it's tied to internal VDD. If you're using a reference, you would set this as a 1 1. You know, here bit 7 and bit 6 will be set as 1 in this stage if you're using an external voltage reference, and then the rest be 0. So here we've got the ADCON1, which that's the next register. All this one is in the 676 chip is this is what sets the clock. You have a sampling clock. Obviously, the more samples you get, so the faster it is, the more accurate you're going to be. Now, again, depending on what you're doing, you may want it to be faster or slower, or you may want to mess around. So what it has is it has the FOSC, which is the function oscillator, which is your main oscillator, so your main clock. Like ours is 4 megahertz, so it'll take 4 megahertz and divide it by 2 if you set this to 000, and so it'll basically be 2 megahertz is what this will run at. Or you can divide it by 8, and then it's smaller, or 32. Or there's also an FRC, which is function RC. What that is an internal RC that they've made, just a resistor capacitor deal. That's an RC oscillator, and it's a 500 kilohertz max internal oscillator. You can choose that if you want to use 500 kilohertz instead of whatever your main clock is. So that's what it says. We're going to use the FOSC by 2. We're going to use the fastest setting. So we're going to set that to 0 here. So we're going to make ADCON1 equal to 0, which sets it to function oscillator divided by 2. Then we're going to turn the ADC on. We're going to say AD on equals 1, which turns the ADC on. Basically right here, the AD on bit. The AD on will turn to a 1. Then we're going to go down to, our next function. That should initialize it, and if you see down here in the main function, we call init A2D, which initializes it, turns it on and everything, sets it up. Then we've got our read A2D. Now, how our read A2D works is we're going to pull in a channel, so as a parameter, so we're just going to use an unsigned int as a channel, and then that'll pull in what channel we're wanting to read. Now, ours, obviously, in our case, will be channel 3, but again, this is just so you have a general function. Also, these functions and whatnot generically are set up again in the High-Tech C's folder that gets installed when you install the High-Tech C compiler. This will be in a file, I think. It's either in a file, but it's in one of the files that's called A2D demo, and these these are basically in there. So basically the skeleton's there. You have to do some tweaking for your chips, whatever chip you chose. Anyway, first thing we do is we see channel and we AND it, excuse me, with a hex 15, basically an OF. So what that does is that takes our channel here and takes the first ones. When we AND it with that, it's basically going to clear anything off of the backside. It's going to mask off to where we just get the first 4 bits of whatever the channel is, and then it masks off the rest of it, so as to not cause confusion. Then what we're going to do is our AD 0, we're going to AND it with OX81, which what that does is 81, it's going to set bit 7 and it's going to set bit 0, but everything else in the middle will be 0. So what that does is that basically is clearing out the channel. It's keeping the ADC on, it's keeping it right justified, as well as also it's keeping our voltage reference set to the internal VDD, but then it's 000ing this all out, which clears the channel. It clears it back to channel 0. And you'll see why, because then the very next step, we OR in our channel that we've read in through our parameter and that we've masked off. We OR it in. So whenever you're ORing something in, it just basically adds it to it. So we want to make sure we clear it all to 0 before adding something to it, because we could, add something in that may not be, if it's already got a 100 and we add 011 to it, we're going to have 111, not 011, So you gotta be careful there. So that's what this is doing. So what we do is we also shift channel 2 places, and the reason we shift it 2 places to the left is because, as you can see up here in our little strip, we shift it 2 places, 1, 2 to the left, because where our channel select is 2 places to the left from here. We don't want to overwrite our AD on or our go done bits. We don't want to overwrite those. We want those to stay the same. So what we're going to do is we're going to shift over whatever channel we've chosen. We're going to shift it over 2 places. That way it lands in the correct space. Okay, so that's why we shift it 2 places and then we OR it in to the AD 0 register. Then we set go done equal to 1. And you know what? I just happened to think of something. The go dones are defined differently on different chips, and I'm going to show you where to go get it. So give me just a second. Okay, let's see. So inside wherever your install directory is, you're going to your program files. If you're using Windows 7 and a 64-bit machine like I am, you'll be in the x86 folder, program files x86. You'll go into high-tech software. You'll go into pick C, and then the version that you're running, that you're using. And then this will be in the include section. And as you can see, there's pretty much every microcontroller you can think of. And what you're looking for is the PIC 16F. And see in here there's PIC 16. What I usually do is I usually just search for it. So I usually just say PIC 16F 676. And voila, there it is. And it's the .h file. So the 676.h file, you open that up. If we open that, which I think default opener is Visual Studio. Yeah, there we go. Okay, I'm going to plop this up here for you guys so you can see it. This has all the definitions of basically keywords that you can use. So as you can see, for your config register, for different config registers, you've got all the different configs that you can put in. All these different words, and it tells you what they do. It's mem clear, or it turns mem clear on, or disables the watchdog timer, whatever. What we want is we want the ADC con 0. So if we search for, you see we've got a comment here. It says register ADC con 0. If you notice, it's got the bit go done is defined like this. I could show you, I'm not going to, but I could show you. If you look at, let's say, the 886, the 16F 886, go done is not hyphenated, or doesn't have an underscore in it. There's no underscore in the go done. Okay, so that can flag the compiler. The compiler will say that it doesn't recognize go done on you, and that's a mishap that you'll run into, is you'll maybe not have it, because I think the original file that you get the ADC out of from their demo file that they should give you does not have that underscore in it, and it will flag it as an error here and say that you're typing in the wrong something it can't recognize. It's an undeclared identifier. So that's when you go to your chip, like in my case it's a 676, go to its header file located in that space that I showed you, and go to the ADCON0 commented portion of it and see what it actually is declared and defined as, and you'll see that it'll be different. And so you type in whatever it's defined as is what you're going to type in for your go done pin. Just some FYI. And by the way, where that one deal where I have to keep talking about that you can get the samples from, if you go to samples, you'll get A2D demo, and so when you get the A2D demo, that's where it is. It's ADC.C is what that'll be. So that's the place where you go to find it. So now you're going to take, and once you do that, you put in your go done. Then we're going to wait while go done. We're going to wait on go done and wait for it to go 0 before we do anything else, so we don't mess up anything. We're going to wait on it to go to 0. Then when it goes to 0, then we're going to return basically what it found. And remember that our format is, where's that at? Our format is here, and remember how our format is, so we need to take that in consideration. And what we're going to do is we're going to take the address high register, which is this one. We're going to shift everything to the left 8 spaces. Then we're going to add to it the address low. So we're going to move this over and add everything to it, so that way we can then output it out. And then we'll return that value, and that will give us our result. So if we get down here to our main function, after saying all that, the rest is pretty simple and straightforward. We're going to take our voltage variable. What I did is I'm strapped for space on this one, and so I don't have a lot of memory on this, so I can't really do decimals very well, because I'd have to use floating point or do some other kind of aggressive ways of not using floating points, but it would require quite a bit of program memory to program all of it. So what I'm going to do is I'm just going to stick with the integer values of the voltage. So I'm going to strip off the decimal value. So what I'm saying is voltage is declared as an integer. I'm saying it's equal to, and what I'm doing here is with the int is I'm typecasting. Those of you that don't know what typecasting does is when you typecast, let's say a floating point number, so like a 2.4, if you typecast that to integer, what that will do is it will truncate the decimal value. So 2.4 will be 2, 3.8 will be 3, 4.6 will be 4. See, it'll just truncate off. It'll only save the integer part if you typecast as an integer. Okay. Otherwise, if you do not typecast this and you try to stick basically a floating number, which is what I'm basically creating here, into an integer, it'll give you a type mismatch error is what it'll give you. So you need to typecast it. And then what I'm doing is I'm taking, remember our 4.88 millivolts, I'm taking whatever the reading is from the ADC and multiplying it by 0.00488, which will give us the voltage representation. Then I'm typecasting that to cut off the decimal. Then what I'm going to do is I'm going to go to position 8, which if you look at voltage and you count the number of characters that are in this, and remember this, the LCD screen counts the 0, so the first character is actually character 0. So 0, 1, 2, 3, 4, 5, 6, 7 is where the colon is. It's in space 7. So that means for me to write the voltage, I have to be in space 8. So I'm saying LCD go to 8, which sends me to space 8, which is the space right after the colon in our voltage, because we've already printed voltage. And we're going to now do a switch case is what I did. Because remember, when you say put CH, it's putting a character. It needs to be an ASCII coded character that it writes to the screen. If you put the number 1 in, if I straight away just throw voltage in there, an integer, and I print an integer, it's going to convert that to hex and send that hex value. So that means it's going to be a hexadecimal 1. Well, you'd have to look at your character map, and what does a hexadecimal 1 get you? You know, it may get you some funky character if you send a hexadecimal 1 to the screen according to the ASCII table. So what I'm doing is, what you would normally do is you would have maybe a hex to ASCII converter or something like that you'd write, a script that you could write. Well, again, I don't have enough space to write something like that and whatnot in program memory for this chip. So what I just did was I just did a switch, and I said switch voltage, so we're inspecting the variable voltage. I'm saying if voltage is equal to 1, then I'm going to print the character 1. I'm going to put CH, then in single quotes I'm putting a 1, and then I'm also putting a V, so it's 1 volt essentially. If it's 2, it's 2 volts. If it's 3, 3 volts, and 4, and so on and so forth is what I'm doing. Then I'm writing all of this inside our control loop. So I like using a for. You could use a while 1 or whatever you want to use as your control loop. But basically your infinite loop. And then what happens is once it gets done printing that out, it's going to go back, read the ADC again, perform the calculation. Then it's going to go back to position 8, so that way it will overwrite what was there. It'll overwrite with the new one. Okay? So remember that you are printing when you put CH and you're putting characters to that screen. They have to fall in ASCII format, because that's how that screen interprets whatever data you send it is in ASCII format. So you can't just print an integer to it. It has to be formatted as ASCII. So that's kind of, I think, all the pitfalls that I can think of. Sorry that this took so long to get out. Hopefully you guys have learned a lot. Again, I will zip all of this up, put it on the project code link that's on my channel. If you haven't checked that out, click on my channel, click subscribe while you're there if you like what you see. But over on the right hand side, excuse me, there is a link called Project Code Link. You click on that, it'll take you to a MediaFire download page where you can download the code that you see here along with those manuals, the schematic, and all that stuff for you to be able to produce this yourself if you would like. There will be a real-life demo coming. I will film that at some point and get that on, and you will be able to see that this code actually does work. This code and that hardware configuration does function and does work, because I think most people get a lot of good out of that, because it's good to see that, you know, I'm not just giving you something and then, you know, you always put it together and then it doesn't work, you know. So I like to show you guys that using the code that I've showed you, the hardware configuration that I've showed you, you put all of it together and it does work. So I'll be uploading that video soon. Videos to come, I will be hopefully doing that HV video, so I'll show the high voltage chips and how to configure them, as well as there might be some more LED cube stuff coming. I don't know, I'm still kind of tinkering with that. I haven't taken it apart yet, so there might be some more videos on that, just different sequences and stuff that you can do. And kind of whatever else we can see. We may look into doing the embedded web server stuff, because that is very interesting. I have to make a board for that though. But cool stuff on the horizon. Thank you guys so much for subscribing, for coming. We're almost to 500 subscribers. Can you believe that? Never in my wildest dreams did I think I would have that many people watching. So glad that everyone has been loving the videos. I love making them. I love helping you guys out in any way I can. So again, questions, comments, you know, PMs, whatever you want to do, get a hold of me if you have any trouble. I'll try to answer you as best I can. Apologize for the delay, but there's more to come. So as usual, keep having fun, keep coding, and it's all about having fun and programming. Take care, guys.